Welcome. We're talking about electrolytic cells today. You can see it's on page 728 to 732. Let me tell you a little bit about something that you already know. You know what we've talked about voltaic cells. Voltaic cells is when we can make electricity from chemical changes. So electrons flow from one side where electrons are hated or they don't have a high electronegativity to the other side where electrons are really loved. And they have this natural flow, a spontaneous flow that they do. So here's an example of a battery with tin and copper. When would the battery stop? When would it run out of working? Well, the batteries don't work when, if you look at the tin, we're losing tin over time. The solid tin is becoming aqueous tin. So when we run out of tin, the battery's dead and it doesn't work anymore. Or on the opposite end, if we run out of copper ions, as the copper ions are moving in to make a copper solid, if we run out of copper ions, then we also don't have the battery running anymore. So when the pieces run out, things don't work. But there are batteries that are rechargeable, so how could we recharge the battery? Well, theoretically speaking, if you can get all electrons to this side, why not recharge it and put all electrons back to where they started, and then we can use it again. And that's the basic idea of a rechargeable battery. So let's take a look closer at this reaction we just saw. This is a voltaic cell. Electrons travel from one side to the other spontaneously. I can see my tin has lost its electrons, my copper has gained those electrons, and so I have an overall cell. Now, if you notice, at the top here, on the voltaic cell we have a voltmeter. It's measuring 0.48 volts. If I wanted to get the electrons to go the opposite way, which is what we see on the right, then I've got to put in just over that 0.48 volts to get the electrons to go back the other way. I'm going to use an external source. That's basically like taking your rechargeable batteries that are now dead because you used them all up and plugging them into the wall. The wall is the external source. The wall is providing electricity that forces the electrons to go where they don't want to go. And this would be an example of an electrolytic cell. It forces electrons back to where they don't want to go. So if you look at the oxidation reaction, it's the opposite one. My copper is now losing electrons. I know my picture's in the way, sorry. But you can see the reduction is the tin one, which is the opposite. And now my tin is gaining electrons, and my overall cell is completely flipped, the opposite. So let's take a look at this idea between what's a voltaic cell and how does it compare to an electrolytic cell. Both of these follow under the big heading that we've been talking about all chapter, which is electrochemistry, the word at the top here. It's a study of the interchange of chemical and electrical energy. How do these two come together? We've been talking about voltaic cells because it takes chemical energy, the bucket stuff, all the ions and atoms, and it creates electrical energy, electricity. Well, an electrolytic cell, it's just the opposite. It's going to use electricity to force chemical changes, that would otherwise not occur on their own. Okay, let's look closely at an electrolytic cell and see the different parts. 99% of all the electrolytic cells happen in one big bucket. And what you can see here is this is just one bucket. We no longer have a salt bridge because it's not necessary, everything mixes together. We no longer have two buckets because we just need one big bucket with all the ions in it. We are going to still have the anode be oxidation because anode and oxidation, A and O, they go together. And the electrons will always leave this side. Oxidation is losing electrons, and so I can see my electrons have lost, and they're headed to the other side, where they have the cathode, still called reduction, and it gains on this side. But one thing we do notice that's different is we do have a battery hooked up, and all batteries have plus and minus ends. We've talked about this, but notice how I've arranged the plus and minus ends here. The plus end of the battery would attract electrons to it, and that's exactly what's happening. The minus end of this battery would force electrons away, and that's what's exactly happening. So I can get my electrons to flow the way I want them to flow by hooking up the battery appropriately, which forces electrons from one end to the other. Another thing to notice is this plus and minus end down here. Now remember, electrolytic cells do what they don't want to do. In other words, electrons move from one side to the other, but they don't want to. So this is an electrode that's a positive charge. It's a positive charge because electrons want to stay here. This part here is where the electrons want to stay. They want to be gained over here. On this part, electrons want to leave. That's why it's negative. I've hooked up a battery to force the electrons over to the other side. So although electrons want to stay here, I hooked up this battery and forced electrons to go to the other side. And although we don't want electrons to go here, I hooked up a battery and forced them to come to this side. Electrolytic cells have things happen that don't want to happen. Okay. All right, here's your assignment to do next. I'd like you to complete this Venn diagram about all the different things a voltaic and electrolytic cell, how they're similar and different, and then complete the Google form. And we'll see you tomorrow to talk more about electrolytic cells.